This chapter is all about gases, and they get their own chapter because they are very different from solids and liquids because of the space between the particles. So vapor is just a gas state of something that's normally a solid or liquid, and normally you'll see this in the terms of water vapor. There are some properties listed here that you just need to be familiar with. You probably learned these in honors chemistry. Again, the big one is that the particles are spaced far apart, which gives them all the properties we're going to talk about. They don't have a shape or volume because, again, you can push them together closer or you can spread the particles out even more, and that would change their volume. And that's different from solids or liquids because those particles are as close as they can get, so you can't really push them together anymore or spread them out. Compressible means that you can squeeze them together. And this is a good definition for pressure. Pressure is the ratio of force per area. But I usually think of it as the number of collisions that the particles have with their containers, because for AP chemistry, most of the time when we talk about pressure, we're going to talk about gases. So if you can picture a balloon with particles bouncing around inside, the more collisions those particles have with the walls of the container or the balloon, the higher the pressure is going to be. So that kind of gives you a visual for what pressure is. Notice the prefix bar. So bar means pressure. So if you take the SAT and you see a word that starts with bar, it probably has to do with pressure. So a barometer is a tool that we use to measure pressure. These listed down here are various units that you might see for pressure, and all of these pressure amounts are the same. These are the amounts that you would see for standard pressure. So again, if you see STP in a question, it means standard temperature and pressure. So this would be the pressure that you use. Now, which one should you use? Well, it depends on what units you want. So if there are other units in the question, like if you're using an R value that we're going to talk about in a minute that has ATM as part of its unit, then you want to choose this for standard pressure so that the ATM matches. And notice that mmHg and torr are the same number. These two are interchangeable. All right, our next section is about manometers. And manometers, it looks like manometer, but it's not manometer, it's a manometer. These are just devices that we use for measuring gas pressure when we're doing some kind of an experiment. So a closed one is going to look like this, where the end of it is closed and the top of it is closed as well. And so this is similar to a barometer where the pressure of the gas is just going to be equal to the height difference between these two levels. So this is, we're going to call this delta H. If it's closed, it's a lot more, it's a lot easier to calculate the gas pressure. It's just the difference in height between those two levels. If it's open, then atmospheric pressure is going to take into account, we have to take into account atmospheric pressure, and so it's going to change the calculation just a little bit. So what you have to do first is to compare the two levels. So notice that in the green picture, the level closest to the gas is lower than the level closest to the atmospheric pressure, where it's pushing in on it. And that means that the gas is pushing pretty hard because it's pushing that level up. Whereas in the blue picture, notice that the level of the gas, it's not pushing as hard on the liquid that's in there, and so that means the atmospheric pressure is greater there. So you just have to use a different calculation depending on those levels. So for letter A, that's what the green picture is showing, you're going to add the atmospheric pressure to the change in height. If it's letter B, which is like the blue picture, then you're going to subtract the atmospheric pressure from the change in height. All right, there's a bunch of gas laws that you learned in honors chemistry, and these actually just let you see the relationships between variables. So we're going to talk about 3 variables in depth: pressure, volume, and temperature. Each of these particular relationships is going to focus on 2 of those 3, and in order for this relationship to happen, the third one has to be held constant. So notice that that says constant temperature, so that means that we have to have the same temperature in order for pressure and volume to have this relationship. The first thing to recognize is the type of relationship that they have. So one little trick that you can use, this goes for math too, if you are ever dividing variables and they're on the same side of the equal sign, look for those D's. If you're dividing the variables, that means they have a direct relationship, which means they'll do the same thing. If one goes up, the other one will go up. If one goes down, the other will go down. If you're multiplying, try to hear the word or the sound at the end of that. It's a Y, but it sounds like an I. Multiply. Think of indirect or inverse, which means if one goes up, the other one goes down. So notice that P and V, we're multiplying them here. That means they're inversely related. So for example, if you have a balloon and you push on that balloon, squeeze it, the volume is going to go down. So the higher the pressure, the lower the volume. And so this just allows us to see that relationship. Charles's law is the next one. Notice that you're dividing these variables this time. V is on top of T, so dividing is direct. So for volume and temperature, that's a direct relationship. And you may have seen this before if you have a plastic water bottle and you leave it in your car in a hot summer day and you go somewhere for a long time and you come back, you can kind of see that the water bottle is busting open almost. And that's because the volume is going to increase as the temperature increases inside there. Oh, this one, be careful though, your temperature has to be in Kelvin. And actually, anytime temperature is on the bottom of a fraction, you need to put your temperature into Kelvin. And the reason is because you may have learned in math that you can't put 0 on the bottom of a fraction. It's impossible, because anything divided by 0 is infinity. You can divide anything by 0 an infinite amount of times. So you can't put 0 on the bottom, and 0 degrees Celsius does exist. In fact, it's the freezing point of water. It's 32 degrees Fahrenheit, so it exists quite often. So we can't use Celsius, we have to use Kelvin. 0 degrees Kelvin is called absolute zero, and it doesn't exist. We've never achieved absolute zero. That would mean that we're getting the particles to stop completely, and we just can't do that. There's always a way for energy to reach the particles, so they're never going to stop moving completely. So absolute zero, 0 degrees Kelvin does not exist, which is why it's okay to use Kelvin there. So just make sure you'll be given your temperature in Celsius because that's what our thermometers are in, and just make sure that you add 273 before you calculate it. Gay-Lussac's law is similar, except we've got pressure. So again, it's a direct relationship. Notice that you have to have volume remain constant. So again, that third thing has to be constant. This is a direct relationship because you're dividing them. You can see that without even having to think about it very hard if you can look for that dividing sign. Again, temperature has to be in Kelvin, and you can kind of figure this one out too, that if you have a balloon and you increase the temperature, which means you speed up the particles, they're going to hit the walls of the balloon more, which means the pressure will increase. So as temperature goes up, your pressure will also go up. Avogadro's law is the relationship between moles, and be careful, moles is the letter N in these equations, between volume and moles. And this one says that if you have constant temperature and pressure, then the volume will be directly proportional to the number of moles. All right, the last gas law for today, well actually two more, is the ideal gas law and then combined gas law. Ideal gas law is the one that you're going to use quite often in this class. Sometimes you hear scientists call it PIVNERT. And it just stands for PV equals nRT. So let's go through each of those letters so you just know what they stand for. P stands for pressure, V stands for volume, N is like the last one and stands for moles, T stands for temperature, and then you get R. And R is actually a constant, which means it is always going to be the same number. It's kind of like the speed of light is a constant. It's always the same speed. And so you will never be given R in a question, and you're never going to be asked for R. They're going to expect that you know to look at your reference packet because it's listed on your reference packet for you. However, there are 3 different choices. So you're probably going to say, well, how do you know which number to choose if there's 3 choices? And the answer has to do with the units. So first of all, take a look at what I have circled in blue. That looks like an equation, and sometimes people try to pretend like it's an equation and plug in liters and ATM and everything in that. That is not an equation. That is just a really big unit. It's kind of like if you're driving and the cop pulls you over and says you're going 70 miles per hour, that's 2 parts, miles per hour. This is just 4 parts. So that's just a really big unit for that number. So the main thing when using this equation, when using PIVNERT, is that all of your numbers need to match the units that R has. So for example, if you're going to use that first R value, 0.0821, your pressure needs to be in ATM because this part of R's unit is in ATM. Your volume has to be in liters because this is in liters. So if they give you milliliters, you have to convert that first. N has to be in moles. So if they give you grams, use the periodic table to get it to moles. And notice again, temperature needs to be in Kelvin. So make sure you add 273 to Celsius. For the next one, 8.31, we're going to use this one later when we get to thermochemistry because joules is a measurement of energy. So when you're dealing with energy, you want to use 8.31 instead of that first number. And then notice this last one, all of the units are the same as the first except for the pressure. So if they give you pressure in torr or mmHg, since those are interchangeable, you can use 62.4. Or you can convert your torr value into ATM, and then you can use that first R value. But the main thing is before you do your calculation, you need to make sure all of your units match what R's units are. Also, make sure that all numbers are about the same chemical. What I mean by that is, if they give you the grams of oxygen and they give you everything else about carbon dioxide, like the pressure and the volume and everything of carbon dioxide, you can't plug in the moles of one thing and the volume of something different. So a lot of times they'll try to trip you up and give you information about two different chemicals, and what you would have to do is to use the multimole ratio and the balanced reaction to convert one of them into the other chemical. You would convert into moles. That's how you would get the N, and then you can plug it into the equation. But just make sure that all of your numbers have the same chemical. Before we do limitations of the gas law, let's go down to the combined gas law. This is actually all of the ones on the previous page put together. So notice if you ignore temperature, then you have Boyle's law, P1V1 equals P2V2. If you ignore pressure, you have Charles's law. If you ignore volume, you have Gay-Lussac's law. So this is all three of them put together, and this is what you use if nothing is held constant. So again, the other three, when you just have two variables, those relationships only work if the third variable is held constant. And if it's not, then you can use this, and you would just have 5 different numbers, and you plug in 5 of the numbers, and then you solve for the 6th one. And again, just be careful with your units. Make sure they match on both sides of the equation. And the last thing is about these limitations of the ideal gas law. Later on in this chapter, we're going to talk about real gases versus ideal gases. So in order to do all of these calculations with these equations, we have to make certain assumptions about the gases, and the assumptions are not really true, and that's why we call them ideal gases instead of real gases. And so the ideal gas law will work the best if you can make your gases as ideal as possible, and the way to do that is when they cannot feel intermolecular forces very well. Because for ideal gases, we assume that they don't have any intermolecular forces, although in real life, they actually do. So if they can't feel those intermolecular forces very well, it's going to make it so that you can calculate these better. And that is the best at low pressures and high temperatures. And I just picture this, actually we'll talk about that in a little bit more detail in class, and I'll give you some examples to help you remember that. But just realize that if it's a low pressure and a high temperature, they can't feel the intermolecular forces very well, and that's going to make it more like an ideal gas. And that's it for today.